Welcome everyone. Thanks for coming for today's seminar. It is great we have Dr. Heping Shen from ENU today with us. Dr. He is now associate professor at ANU, where she's leading a research group focusing on developing of next generation and ultra low cost solar cell technologies, including Perovskite and Tandem solar cells. She was recently awarded the IEEE Stu Wenham Young Professional Award. In the past, IEEE in Canada. She has been working on PV for more than 15 years, and she got her bachelor degree from Huazhong University of Science and Technology and her PhD from Tsinghua University. She has published over, I think, 100 journal papers, including top-tier journals, including Nature Science and Nature Material Review. Very impressive track record. Today, she will talk about was cost-effective perovskite silicon tandem solar cells based on passivating contact silicon solar cells. Let's welcome Dr. He.
First of all, thank you so much, Kevin, for the invitation and also the organization. I'm very, very happy to be here because ANU and UNSW, we have been having close collaboration for decades and making both domestic, national, and international contributions in the PV field. And also thank you all for taking your time to come here. I know funding applications are very important, so I'm very aware of that and understand that. Yes, I see a lot of friends here, very happy for that. And I'm also very happy today. I would like to have this option to share with you our journey and some of our key work that we have done in the past few years to contribute to the development of the cost-effective perovskite and silicon and tandem solar cells, particularly focusing on commercialized TOPCon cell technology. And majority of the work were done through our close collaboration with our industry partner, Jinko Solar, which I think I don't need to introduce too much. Okay. I assume that if not all, probably majority of you are from the PV field. I'm not sure whether I'm correct. Anyone not from the PV field? Looks all of you have the background of the PV. So for me to introduce the tandem, and I guess I probably don't need to have too much background discussion and sharing. And for the tandem solar cells, there are different cell structures. The majority of these, including the 4-terminal tandem, where we stack the two subcells together without electrical connection. We also have another mainstream that is the 2-terminal monolithic perovskite silicon tandem solar cell structure, where we use the interconnect layer to connect the two subcells into the same piece of devices. And also, we also have the 3-terminal tandem. I guess you may have heard from lots of places. They all have their own advantages and disadvantages. So for which, again, because you all have the PV background, you have experience in the PV. So I won't take time, waste time to discuss too much basic information. Instead, I will dive directly into the technology directly. At ANU, we, over the past decade, particularly for past 5 years, we have been devoting efforts both into the 4-terminal perovskite tandem solar cells and also the 2-terminal tandem solar cells. For both, we have been able to achieving state-of-the-art result that is among the top world-leading performances. And because of the time, I won't be able to introduce both, but I will focus on the monolithic 2-terminal perovskite silicon tandem solar cells because of a few advantages of this technology. First, I think it's simplified structure where we use less substrates, and thus we will possibly have high efficiencies. And also the potential compatibility with the commercial silicon modules. a few others. Of course, it has its own challenge. We will discuss later. Okay, then on the page here in the middle is a illustration showing the basic structure of a two-terminal tandem solar cell structure, where you can see a top cell is connected with the bottom cell using an interconnect layer. This interconnect layer not only provides optical coupling between the two subcells, but very importantly, provide the electrical electrical connection between the two subcells with a minimum electrical loss. So beyond this, there will be the top and the rear contact that will are necessary to extract the charges out of the cell. To develop a cost-effective tandem solar cell, we think it's essential to take a holistic approach to focus not only all of the components here, which is 5 components here, but also integrate them into the tandem level for systematic optimization. So that is also the approach we at NU take to develop a cost-effective tandem solar cells. Today, my topic will be focusing on 3 key aspects. So this will be, you can see on the figure, the blue part and the red part, which are the 2 essential components, the efficient, stable, low cost top and bottom cell. As well as I will introduce you a few, particularly one of the very innovative interconnect design for a tandem cell structure. Okay. So with that, I will dive into technical details. First of all, one of the key, very important questions that remains to be answered and open at the field now is, what is the potential feasible and maybe the most potential bottom cell technology that can be used as the bottom cell in the tandem? For the silicon, the question would be TOPCon and the silicon heterojunction, which will be more promising for being used as a bottom cell. So if we look at the market share here, which all of you might be very familiar with, is that looking forward for the next decade, the PERC solar cell, which has good market now but will diminish in the next decade, has not only because of not only the market will diminish, but also there is challenge of using this technology into the tandem, particularly for the monolithic tandem, because of the use of the insulating passivation layer and therefore the point of contact. So that is remaining challenging for being used for the two-terminal tandem. But beyond that, there are 2 more promising passivating contact silicon technologies. One is TOPCon, the other one is silicon heterojunction. Both of them remain very promising for being used as a bottom cell in the tandem cell structure. And both of them will have expanded market share. And particularly for TOPCon, in the next decade, it probably is safe to say that it will be staying as a main contributor for the PV market. So that's the market. And then further assessing the suitability of a solar cell technology in the tandem cell, we further assess it from the few key aspects, metrics that we usually use to assess potential success for solar cell technology. That is the efficiency, the cost, reliability, and also the sustainability. Let's look at the efficiency first. For the TOPCon and silicon heterojunction, at the single junction level, the efficiency are getting very close nowadays. If we look at the record efficiency, single junction TOPCon, which is 26.7, is very close to 26.8 by silicon heterojunction. Both of the cell performance were demonstrated by industry reliable, large PV companies. And on the other hand, if we also look at the evolution, performance evolution of these 2 technologies, for example, if we look at the open circuit voltage of these 2 technologies, we find that their performance are converging. The VOC are very close to be locating at 740 to 750 millivolt range. So it's clear that their single junction efficiency are getting very close. If we look at the efficiency at the tandem level, here I show you a efficiency evolution of the monolithic perovskite silicon tandems based on different silicon technology. And you can see that it's very clear that the BSF and the PERC, which I mentioned briefly just now, which is the green and the blue color, are not much developed right now, because not only because of the inferior performance, but also because of the challenges I mentioned in terms of integration into the two-terminal tandem. Silicon heterojunction and the TOPCon both have been able to, till now, achieving high efficiencies, 33 to 34 range, well beyond that silicon can be achieving. But silicon heterojunction have been historically, particularly in the last decade, dominating in the perovskite silicon tandem application, so therefore leading the efficiency record. But this picture changed over the last 3 years. As you can see, a lot more red dots, which is a tandem based on TOPCon, are coming up, and the efficiency are also progressing very fast. Although their first report was demonstrated only a few years after that, based on heterojunction solar cells. Okay, with that, I believe it's clear that for the TOPCon and silicon heterojunction, both high efficiency passive condensed silicon solar cells, they remain to be highly efficient, and also the efficiency are very close, both in the single junction and also the tandem level. Okay, moving on, we'll look at the cost, another very important matrix. I think I don't need to explain too much that the TOPCon still retains significant capex advantage versus the silicon heterojunction. And at the tandem level, let's look at how it looks like. So this is a techno-economic analysis done a few years ago by Fraunhofer by comparing the tandem cost based on different bottom silicon cell technology. As you can see, we have PERC technology, we have TOPCon and double-sided TOPCon, as well as silicon heterojunction. That cost, as I said, it takes into consideration of both the efficiency potential as well as the realistic industrial manufacturing cost. Indicates that the tandems based on TOPCon cell structure, either the one-side TOPCon or the double-sided TOPCon, shows considerably lower cost, dollar per watt, compared to that based on silicon heterojunction-based tandems. So because in the last 3 years, there have been further fast progress, efficiency progress of the tandem based on TOPCon, we reckon that figure, that difference will be even more. So with that, it's clear that from the cost perspective, the TOPCon and the silicon junction has a clear advantage compared to silicon junction, both in the single junction and the tandem level. Okay, and moving to the next important aspects, we are looking at the triangle of the a golden triangle of the solar cell, right? So the stability. So here I would like to mention an important stability aspect, which is the thermal stability. TOPCon shows clear better thermal stability compared to that of the silicon heterojunction. TOPCon can be stable up to 400 degrees above, but silicon heterojunction will degrade when the temperature is above 250. So this feature is very important. That's because on the first hand, for developing the perovskite silicon tandems, so there are various processes in the perovskite fabrication that may involve high temperature. For example, the highly efficient functional layers like charge transporter layer, nickel oxide or titanium oxide, or the very thermally stable perovskite compositions like fully inorganic perovskite, which requires more than 300 degree post-treatment to allow a phase stable perovskite. So for the perovskite silicon tandem, that's very important. And at a big picture, it's also very important for developing the tandem, silicon-based tandems on other potential tandem technology like thin film, which also usually involves the high temperature process. So we think that's very, very important and give TOPCon another advantage compared to silicon hydrogen from the stability point of view. Okay. Final aspect we also assess is the sustainability. This is, of course, becoming more and more important because we are transitioning towards the terawatt regime of the PV deployment. So actually, so there are two key elements used, critical materials that are used in these solar cell technologies we look at. And there are some simulation results, the results that actually have been was done by UNSW Brett's group. I think some of the researchers are here to assess the impact of the use of these critical materials on the production capacity of different technologies. So one is silver. We know that TOPCon has used less silver compared to silicon heterojunction. So assuming a similar level of the silver supply, so we would be able to have significantly higher production capacity for the TOPCon compared to silicon heterojunction. If we put the number here, so 230 versus 170 gigawatt, that's significant difference. On the other hand, for the use of the other earth rare element, indium, so we know that heterojunction solar cells use a lot of TCOs, which usually involves indium in its transparent conductive oxide material, which is absent in the TOPCon cell. So if we're assuming like 20% of the global indium supply will be used for making the solar cell, so unfortunately, that poses another significant constraint for the production capacity of the silicon heterojunction to even less, which is around 30 to 90 gigawatt. So with that, I think with that together, from the efficiency, cost, stability, sustainability point of view, we see clear advantage of using TOPCon cell technology versus compared to using silicon heterojunction. And also another important factor here I mentioned in the beginning is the market. Okay, so I hope till now you agree with me that it's important to develop perovskite silicon tandems based on TOPCon technology. Okay, with that, I will move on to share with you some of our key work that we have been done and contributing to this field. Again, let's look at this efficient chart, which looks busy, but here you can focus on the red dots here, which shows the evolution of the tandem based on TOPCon solar cell technology. And I will start with the first dot here, which is the first report of the tandem, perovskite silicon tandem, based on TOPCon cell in the two-terminal tandem structure. And that was first reported by ANU back in middle of 2018. Okay, let's look at this structure. I will provide you more details about this structure. As you can see here, this is a cell structure. At the bottom is a silicon solar cell using N-type wafer as a bulk and also P-type polysilicon as an emitter on the front. At the rear side is a silicon nitride passivation with a localized contact here. And to pair with this cell structure, we use a NIP perovskite solar cell based on titanium electron transport material. So these two cells make a tandem. So as we can see, so this that was the first time that TOPCon is used introducing the tandem, but also is a P-type TOPCon that is used. And that time we were able to demonstrate 24% efficiency for the proof of concept device, which is not only very high for this cell structure, but also I believe is among the highest for any two-terminal perovskite silicon tandem based on any type of cell structures. Okay, so this is the one feature is introducing the polysilicon into the tandem cell structure. And another very interesting cell feature, an innovative feature in this cell structure, is the use of a novel interconnect design. Here, I would like to give you more information. As I mentioned previously, the two-terminal tandem solar cell is usually by connecting the two subcells using an interconnect layer. So this interconnect layer could be the tunneling junction or the recombination, like the transport connect, the TCO, like ITO or IZO. But in this structure, if we look closely here in the interface between the two subcells, you will find that there's not any interconnect layer here. Basically, we put the TCO, the perovskite solar cell on top of the silicon cell directly without the need of any interconnect layer. So it's like showing in the middle here. We don't have TCO, we don't have tunneling junction. So this is the first time that this cell structure was proposed and demonstrated and proven high efficiencies. And we named it as an interconnect-free tandem cell structure. And this structure is very interesting and also very attractive in terms of few different aspects. First, it simplifies the structure, right? We don't need to deposit any tunneling junction. We don't need to deposit any TCO layer. We just place the two cells together. So it simplifies the cell structure. That means it can possibly reduce the cost. And it can have a higher efficiency potential by eliminating the potential parasitic absorption loss from this tunneling junction or TCO layer. So this is proven by the high efficiency we were already able to achieve. And third, it's quite beneficial for upscaling because we deposit this ALD titanium layer on top of the P+, and this ALD layer is quite dense and also not very laterally connective. So it avoided the potential shunting that could come in from tunneling junction or the recombination, which will become a big problem when upscaling. So it has a few important advantages here so that we keep on understanding how this structure could work, because it's a surprise to us, as usually the titanium and P+ silicon would form the junction that having the rectifying, behavior that shouldn't allow us to have a good ohmic contact in between, which is indeed the case when we use some of the conventional titanium we developed in our lab. As you can see from this contact testing IV curves here, like this bright blue color, and they are rectifying. But for some certain smartly engineered titanium material, we find that it can give us such a low resistivity ohmic contact between this titanium and the P+, and it is such a contact that enables us to have a good performance for the tandem. It is such an interesting, innovative structure. So then we move on to understanding the mechanism behind that and try to correlate our experiment result with our simulation result. And we found there are a few important physical parameters that makes this performance, this behavior possible. The first one is the energy alignment between the titanium and the silicon, particularly the energy difference between the connection band of the silicon of the titanium with the valence band of the silicon. So that energy difference, delta here, we find that when this energy level difference is low enough, that will allow us to tend to have a low resistive contact. And on the other hand, the doping density is also very important doping species. Species also plays a role. For example, for the P+ silicon here itself, we find that when we enhance the doping density to a level that is about 1020 or 1020, even to the regime of 1021, that allows us to have such a low resistivity contact. Okay, putting this hypothesis and understanding into the figure is that, okay, when this energy level difference delta here is low enough, we reckon this recombination happens on the atomic interface here through these defects on the interfaces that allows us to have an effective and efficient recombination and thus efficient tandem. So this theory is very, very helpful, not only for us to understanding the cell, how the cell works, but also helps us to explore new materials and the new cell structures that could work, which we expand actually to the PRN and also some new dopant-free silicon bottom cells. And also, it allows us to further optimize this structure to higher performances, which I will share later in my seminar. Okay, so that's the first work I like to share. The first report on the P-type poly into the tandem, the first demonstration of innovative interconnect-free tandem cell structure. And then move on. In 2022, there's another prominent technology I like to share with you. That was the first report of the monolithic perovskite silicon tandem on mass-produced TOPCon silicon cell from the industry. So we done this work. We did this work in collaboration with our industry partner Jinko Solar. Basically, we grabbed the silicon cells from their production line, and we developed the perovskite on top of it for the tandem. So at that time, we started with demonstrate tandems on the planar structure. Although planar, they are not planar like our lab level planar. They are still quite rough. At long distance, millimeter level distance, the roughness could be up to micrometer level roughness, from the highest to the lowest. So we cope with that challenge because our perovskite is only hundreds of nanometer. So it is quite challenging to have a high performance perovskite on top of it. So we cope with that challenge by developing the conformal nickel oxide layer together with some passivation layer on it. And in the meantime, we optimize our perovskite fabrication process in a way that can have a good conformal layer on top of this rough surface. At that time, we were able to demonstrate 27.6% efficiency. And another important innovation in this work is that we replace the conventionally used anti-reflection layer based on magnesium fluoride into this silicon oxide PDFE composite to allow a better prohibition of the penetration of moisture and oxygen, because these layers show much better coverage and much fewer cracks in their film itself. Okay, so that's our first report on the tandem on TOPCon. But we since then we have been moving fast in this field, as you can see in the evolution chart later. So we keep on optimizing. There are a lot of optimization, as I mentioned, at the tandem level of electrical optimization. Indicated by our PL study, we found that interfacial recombination between perovskite and charge transport material are a major loss sources in our tandem cell. So we spent a lot of time to explore the new passivation materials and engineering these passivation processes in a way that we further improve the performance and reduce the recombination on these interfaces, and which allows us to achieve more than 30 and 31, 32% efficiency. And one of the notable field metrics here is very high field factor. We achieve almost 87% field factor in these high efficiency cells based on commercial mass-produced TOPCon cell. I believe that should be among the highest that has been reported. Okay, so that's the electrical optimization. And simultaneously, we have been doing the optical optimization, particularly by using some texturing silicon substrate, majorly focusing on the nano texturing, which means the texturing with the size of roughly 1 micrometer or less than 1 micrometer. So for that we we did a lot of work in collaboration with our industry partner Jinko, and then I think that also allows us further improvement of the cell performance. That is reviewed by the recent record efficiency by Jinko in the using Tandem based on TOPCon, which is up to 33.9% efficiency. Okay, so I believe there's still significant a good room for further improvement of the cell performance based on mass-produced TOPCon. So hopefully we can see more progress very soon. Okay, let's move on to till now I've introduced the work on using p-type poly into the Tandem and the commercial TOPCon, which is n-type poly, into the Tandem. And another piece of important work in terms of developing high-performance tandems is by integrating both p-type poly and also n-type poly into the tandems cells. So we proposed this idea back in 2020 and did simulation for that to understand the benefits of using this structure in the Tandem. And we were at that time we demonstrated over 32% efficiency tandems using this structure based on NIP cell structure we have been established in our lab, and proposed the possibility as well as the strategies for achieving that. And inspired by that, we then in the lab focus on developing such structure using some industry relevant process. So if you will look at this bottom TOPCon, double-sided TOPCon cell structure, that is the final structure we use, where you can see this is the silicon wafer, and each side is, one is n-type poly, the other one is a p-type. It's very like heterojunction, but it's it's a TOPCon passivating contact. And on top of each other, we have some barrier layer we call titanium on top of it. Of course, depending on how we use these cell structures, we will deposit the electrode on top of it. So we were able to demonstrate, achieve these cell structures using not only industry relevant processes, which we use the LPCVD method or PECVD method, that is widely used for the TOPCon cell structure, but also a streamlined process where we can finish the cell structure in a very short time, like half a day or something. Very nice cell structure and fabrication flow. And the other few features of this cell structure, as you can see, that it doesn't have silver in the cell structure. We use aluminum as a contact in the cell, and of course, it doesn't have TCO in it. We don't need any TCO, so it's. I think I don't need to emphasize the advantage of that again. Of course, the high temperature tolerance is another factor, and because of its symmetric structure, where you can see here, very highly symmetric, so we can also use that both in the NIP and the PIN tandem cell structure. So that's indeed what we have been doing, and allowed us to have high performances. But because of the time limit, I will focus on the NIP cell structure again in my topic here today, because of that innovative, the interconnect-free tandem structure. Okay. So here is again we can see the bottom is a double-sided poly, as you can see. The P plus is used on the top, and on top of it is titanium, right? On the rear, we have the n-type poly, and again, the titanium as a barrier layer, and we have the aluminum as a contact here. Again, we utilize our interconnect-free tandem structure, where we have been pioneering over the past few years, and to further demonstrating the application of this double-sided poly in the tandem. And in this cell structure, NIP, there is a long-lasting challenge in this cell structure, particularly related to the HTL site, which is here on top of the perovskite, which is a layer that is used for whole transport. So there are a few criteria we need to meet for such an efficient whole transport material. First, they need to be highly transparent to allow minimum perovskite absorption loss. They have to be very conductive to allow a good performance. They have to provide favorable energy levels. They have to be stable. So we were trying to find some material that can meet all of these criteria. And unfortunately, the widely used spirometallurgical material can allow a good efficiency for the single junction, but have a lot of challenges in terms of these aspects. So it has, for example, it has very low mobility, 10-5 or 10-4. That means we need dopant to allow it to be highly conductive. We usually use lithium salt or TBB, some organic molecules. So this causes a significant problem in terms of stability because they can migrate easily in the cell. Together with the low crystallization temperature of spirometallurgical, their stability is a big problem. And also they are usually very thick. 120 or 100 nanometer is the minimum we can have through the solution method. So that causes a significant loss for the current because of the absorption loss up to 2 to 3 milliamp. And of course, the energy level we found also not ideal, particularly for the wide bandgap perovskite solar cell we are developing. On the other hand, we explore different materials and identify spiral TDP as a potential material candidate to replace this material. It has 1 to 2 order magnitude higher mobility. That means we have the potential to have conductive HDL layers based on this material without any help from the dopant. So it addresses a lot of the stability issue from the dopants. It's stable up to 85, which is the temperature we usually can see for the solar module, and can be up to 100 degrees, which of course need to be further assessed. And also it has a higher water angle that allows us to prohibit the penetration of the moisture into the cell. And they can be deposited through the thermal evaporation method, the vacuum method, for which we can deposit ultra thin layer. With that, we can minimize the perovskite absorption loss to a very low level. And its energy level is also found to be better, which I will share a little bit later. Okay, so that is our analysis and our justification for using this material into the Tandem to replace spirometallurgical. And in our real device development, we found that it indeed gave us great performance together with the stability as well as the optical advantages we have claimed just now. At the single junction level, as you can see, this is a cross-section of the cell structure where you can see the layer is really ultra thin, 8 to 10 nanometer, covering very well on this perovskite layer. And we were able to demonstrate comparable cell performance using this spiral TDP compared to spirometallurgical for the wider band gap. And in the meantime, we further improved the cell performance by inserting another dopant-free layer to make a double layer, which further improved the VOCs and fill factor that allows us to have better performance because of the better energy alignment here. As you can see, this is the perovskite, right? And this is wider band perovskite we have, and this is a spirometallurgical. The valence band difference was huge, was relatively large compared to when we use spiral TDP and poly TBT. So then we move on to understand how this energy level is important and benefit our cell performance. We again do the simulation to understand that. We found that this ionization potential of the HTL indeed impacts significantly on the interfacial recombination as well as the whole conductivity on the perovskite and HTL interfaces. Okay, so then we move on to applying this cell structure into the Tandem using the NIP cell structure. And we were able to produce quite impressive efficiency based on the double-side poly and also the NIP cell structure. And particularly, we were able to demonstrate current density of above 90, which is significantly higher than most of the cell structure using spiral omitted, which is 17 or 18. And the field factor is quite attractive. So over 29% efficiency, that was the highest for the tandem based on double-sided poly, but also I like to share that that's also the highest performance based on the NIP perovskite cell structure. So this I won't discuss too much about details. We can of course take that into discussion later in the Q&A session. But this is another important open question that need to be answered, which is the tandems, whether on NIP or on the PI, because both of the structure have their own advantage, but also their own challenge. For example, PI, which is a major technology that people have been focusing, has their challenges of also the relatively high absorption loss from the carbon-60, which is usually used as electron transporter material on top of the perovskite, but also the mechanical instability from this, carbon-60 and also the perovskite layers. I think, but the thing is that both of the NIP and a tandem based on NIP and PI are progressing fast, and there seems to be no sign that any of the cell structure performance will be, stopping. So I think NIP with the significant, like the long-lasting bottleneck here for the HTL being addressed by using some innovative material, we believe there is a great future for tandem based on NIP cell structure, and we were fortunate to producing this the highest efficiency based on this structure, and we will keep on improving that. Okay, till now I have introduced the tandems based on different TOPCon polysilicon technology. I've introduced the interconnect-free tandem cell structure we proposed and we pioneered at Australia here. We also talked about the NIPPIN. All of these contribute to the fast development of the cell performance to a level that is very attractive. That is the efficiency. But of course, for the tandem, for any type of tandem cells, the stability and also as well as the scalability are the major challenges we need to cope with to allow it to be commercialized. So stability definitely is the most obvious hurdle here, although we see fast progress in terms of the stability too. In one of our previous review and perspective paper, we summarized the stability of the perovskite silicon tandem versus the single junction. We found that actually the tandem stability is even more, more challenging compared to the single junction. If we look at the measurement time, we can see that, for example, the red dots here on this curve, that is the tandem, and the blue is the single junction. We found that the stability measurement for the tandem solar cell are much shorter compared to those based on single junction. For example, for single junction, the stability tests are usually above thousands or sometimes tens of thousands of hours test. But for the tandem solar cell, it's like hundreds of hours measurement usually. That can be found in the literature. That's significantly lower than the single junction, but also significantly lower than what we require for industrial stable cell. And that's one thing, one challenge. The other gap is that there are very limited study on the tandem stability under heat as well as light. And of course, the combination of those are very rare. So there are still a big gap here for getting, the tandem stability assessed and also understood. So we provided some fundamental understanding about the fundamental theories behind the instability of these tandems, for which, if you are interested, feel free to read the paper. But there are three key things we think that need to be highlighted. Of course, having the proper standards for testing the stability is, of course, the very important, and understanding their degradation mechanism is also in parallel very important to help us to further improve the stability. Of course, is very clear. So that's what we have been focusing over the past few years, particularly using the state-of-the-art tandem cells we developed in-house and in our collaboration with our industry partner, Jinko. And we grab some of the highly efficient tandem cells, which usually have the initial efficiency above 30%, and then we encapsulate them using some optimized encapsulation, incorporating both the edge sealing and also the field sealing that more or less mimic what we have been done using for the silicon commercial cell, but with some modification of the material and process. And we tested first against the IC standards that are set up for the silicon, and we found some of these cells are very showing some promising stability because of our encapsulation as well our cell optimization. So, for example, we are able, so our tandem cells, these highly efficient cells, can pass to IEC stands for damp heat, and can pass to IEC standards of the thermal cycling. And also they show quite a good stability, very negligible performance loss, probably less than 2% on the MPP tracking on the light. And also the UV exposure doesn't give them too much degradation. So these are very recent results. We haven't published yet, but that give us much confidence, in terms of further improvement of the perovskite silicon tandem solar cells. And of course, we don't think that's necessary. That's enough. We need to keep on not only extend these tests, but also having some outdoor stability. Actually, for which we are collaborating with UNSW in these aspects. So that's what we are doing. And the final aspect, I will very briefly touch base on the upscaling. So this is a review image from a review paper on Tandem. To summarize the performance of the Tandem, perovskite silicon Tandem, on different size, as you can see, size from 0.1 square centimeter to 1 centimeter 10/100. So there are two gaps here. First, we can see that majority of the reported results are still on small area, usually 1 square centimeter. That is significantly lower than what we require for the industrial cell size. Unfortunately, in this 100 above 100 square centimeter, even above 10 or 20 square centimeter, there are very little report here. So that's a gap here. And second, if we look at the average efficiency, there is also significant efficiency drop from during the upscaling, from upscaling it from 1 square centimeter to 100 square centimeter. For example, averagely 1 square centimeter we can get 28-30, but at 100 square centimeter that's only 22-25 maximum. So there is significant loss. So that's because majority of the research are still focusing on the non-scalable spin coating method for the perovskite. So which is very challenging for scale up. So there are multiple ways that can address this problem. For example, we can use still the solution-based method like blade coating or solid coating, which shares similar chemistry theory. We can also using some evaporation and the solution hybrid method. So that is the efforts we are devoting at ANU to here, and we have been able to demonstrate some promising results through extensive engineering of the perovskite compositions as well as the deposition process. For example, using blade coating method, we were able to get comparable cell performance with that of the spin coating. So now we are just using this technology on the large area, over 100 square centimeter tandem cells to demonstrate high efficiencies. So hopefully we will have more results I can share with you in the near future. Okay, with that, I think I'd like to conclude my presentation. So the tandems on TOPCon is very important, gives us various advantages across all the metrics we look at for solar cell technology. And ANU and in collaboration with our industry partner have contributed a lot nationally, internationally in this field to progress it to a level that is comparable to the tandem based on heterojunction. And ANU and Australia, we are pioneering a novel interconnect-free tandem cell structure, and it's still progressing fast. It has a lot of advantage in terms of efficiency, simplify process, and also scale up. And we also address a long-lasting bottleneck for the NIP, and we're able to produce a high efficiency based on that. And of course, stability and upscaling are the major focus we are working on, and they are progressing fast and turning to be more and more promising. But of course, they are still challenging. We need to have further work, collaborative work with UNSW on these aspects. With that, I'd like to thank you all for listening, and also thank for our whole team at ANU. I'm very happy to answer any question if you have.
That's a nice talk, very impressive results. Do you have any question from August? Terry.
Hi, yes, a very nice talk. A lot of nice information, and you can see the sort of the growth over the years. I think just a few questions. So I think in one of your earlier figures, you showed that sort of the efficiency for TOPCon, or the VOC for TOPCon, is sort of catching up to the silicon heterojunctions. Do you expect maybe in the next few years that actually might pass that of the silicon heterojunctions?
That's a great question. From my understanding, theoretically, I think theoretically, at least I didn't see any theoretical prediction to showing that TOPCon will be necessarily having higher VOCs or performance than silicon heterojunction. I would say they will be becoming more and more comparable, but existing that seem to be something that need to be further assessed.
And yes, so another question is, obviously over the years there's sort of been a competition between the PIN and NIP. Mm-hmm. So with say NIP, for example, obviously you use like TiO2 or tin oxide, for example, for the electron transport layer. And then for PIN, it's they end up using C60, as you mentioned. So it's also tricky to look at sort of which one is sort of better, because PIN, they've also used self-assembly molecules, which is much better for in terms of parasitic absorption. Whereas in your case here, you've used Spiro TTB, which is, and same as Spiro Omitad, as well as poly TPD, which are more, I guess, parasitically absorbing. So are there any sort of new materials, have people come up with sort of new materials to sort of to use for the sort of P-type, the P-type whole transport layer?
Oh, okay. Yeah, that's really great question. Yes, that's actually, you have provided a lot of information that add to my statement that say, for PIN and NIP, I think they all both have their own advantages, but also their own challenges. For the PIN, for your particular question, in terms of the, to replace carbon-60, which is a big problem for not only the absorption loss, but also for the mechanical stability. So one of the structure I believe that might be very promising and has been proven to be working efficiently is just completely remove the carbon-60 using tin oxide direct on top of the perovskite. I believe there were one or two very nice papers published on that, although their performance are still inferior compared to using carbon-60, but they are proven to be working, so that we can completely use the inorganic HDL, completely remove that absorption and also the stability challenge. But also, on the other hand, for the PIN, I agree. I think another challenge is that, yes, some self-assembly materials, they are very nice in terms of pursuing high efficiency, reporting record efficiencies, but in terms of upscaling, it will be very challenging. Assuming a SAM layer which is only one molecular at hundreds of square centimeter, a few square meter, that will be, I reckon that will be a significant challenge, which also is what we see in our lab. So we always think it's very important to have an inorganic layer there to allow the upscaling, maybe with the assistance of this SAM, but probably not solely with the SAM.
Okay. Yes. Great. Thanks. I think it also goes up to the fact that if you go upscaling to larger sizes, it becomes a lot of you run into a lot of challenges. So yes. And also thanks for citing that paper that you cited with the larger. So thanks for citing our work as well on that.
Oh yeah, great.
Actually, I have a question about the top with bottom connection method. Basically, you have two methods. One is so-called interconnect free. But you also still using your ITO between the silicon and the perovskite solar cells. Can you comment the two methods, the pros and cons?
Sure.
How do you see the future of them?
Okay. So first of all, yes. So with some of the structure, we use the interconnect free because that's the time when we find this particular structure, titanium and the P+ works, because this is an innovative structure. Not all the the material couples would work. So for the NIP, we found this structure, but for PI, when we try to use this interconnect free structure, it's not that natural. We require a lot of extensive optimization of the material engineering on the interface to make it happen. So actually, not until recently, we were able to actually demonstrate this also interconnect-free tandem on PI, but we haven't. We are still in the process of further, improve the performance. So that's why before that we have been using the standard interconnected existing structure, right? Standard conventional structure. Okay, so that's the reason why we have different structure. And then in terms of your question asking the potential or the difference of this structure, I do see, as I mentioned, I do see the advantages of using this interconnect-free structure, right? We don't need, for tandem, it's already very complicated. We have more than 10 or maybe 10 or 15 processes. Eliminating any of the, process will be very, very helpful and desirable for the cell fabrication. And also this TCO layer, all tandem junction, none of them are transparent. All of them will be absorptive, right? So if we can take off this, the advantage seems to be very obvious to me. And second is that, I mentioned about the scalability. So particularly for that structure, you can see here, because for TCO layer, for example, for tandem junction, whatever we make, there is they are relatively highly conductive laterally. So that means if there's any pinholes in this layer, that will be coming the source for the shunting. And unfortunately for this TCO layer, or the tandem junction, if you have a fabrication experience in the lab, you will find that sputtering method, deposited, TCO will very highly possibly have this shunting and these pinholes. It won't be very complete like ALD. So this possibly, I think we will be having some challenge. But the structure I shared just now, we have the ALD titanium. Titanium itself is very isolating and it's ALD layer deposited. So it's very dense. So that at least avoided the risk of being shunted at the large scale. So we think that's another advantage. So that's also what we are assessing in the large area.
That surprised me, the titanium oxide, between the top and bottom cells, you can still connecting
exactly
with each other.
Yeah, we have the same kind of feeling with you. We think this is very surprising, interesting structure. Yeah.
Any other question?
Yeah, thanks, Heping. Very nice talk. About the I think it's bottom cell is P poly. That one, I know like us, we're also working on that. I mean, for NU has like published papers on the p-poly quality improvement, right? So, for the bottom cell, any specific requirements for this p-poly and on the top, right? On the top of the bottom cell. Normally for TOPCon, there's n-poly on the back, but you are using p-poly plus titanium oxide as kind of tunneling, right? So for p-poly, any like requirement for that? You mentioned about the conductivity, the energy, the band alignment, right? How about the passivation for p-poly? So, and also it's not really transparent, right? So, I mean, in the longer wavelength, you still have this free carrier adoption from p-poly layer that is called dead layer. You will lose some of the current. So, yeah, what do you think? What do you see from the silicon side? I mean, probably you mentioned that your bottom cell come from your partner, right? So any like specific design for that as well for the bottom cell?
Okay. So first of all, I think I introduced three different structures here. So the major, the major takeaway information is that both the P plus poly and the N plus poly can be used solely in the tandem structure, which actually allows us to integrate different perovskite cell structure, which actually there are a lot of different structure into the tandem. Even if we combine both, that's also possible. And in terms of, I think there's another question in terms of the P plus poly, in terms of passivation. The passivation of the P plus poly is still inferior compared to that of the N plus poly, but both from industry and also our lab progress, we find that gap is also getting smaller and smaller through our optimization and understanding of the theory. So that means, and also particularly for the P plus.
That because you are incorporating this tandem structure, the interlayer of the P-poly, the passivation is not that critical?
No. It's still critical. So it's still critical. This passivation of the P plus poly is, is not coming from is isolated from the top cell optimization. It's solely based on our P plus poly optimizing in our lab itself. So that kind of passivation is common to some level for both single junction and the tandem. It's isolated from the titanium on the top. But what I want to say is that because anti-poly is already very well developed, so I don't think there's a big gap compared to the heterojunction. But P plus poly has been there has been some gap there, but there has been also significant improvement in terms of P plus poly in our lab. That is at least that exists. That seems to be better than the PERC technology we have been using the ALOX and the silicon nitride passivation. But of course, I think there are still space here to further improve it to a level that is comparable to anti-poly. And in terms of another question, in terms of the optical assessment, so I think the optical loss, parasitic absorption loss from heterojunction, HAT, and also TOPCon are both could be a problem if we don't address that or tailor that in the tandem. For example, heterojunction, although the amorphous silicon is very thin, but the TCO layer is very thick, right? You need to thin down the TCO thickness or even optimize your amorphous silicon layer. For TOPCon, the same. TOPCon, if we use on the front, yes. If we use the commercial TOPCon cell, that will be significant optical loss. Particularly the TOPCon will be around 150 or even thicker TOPCon. But of course, there are some tailoring modification into that poly into thinner. In the meantime, we are also developing even thinner poly. For example, we use 40 nanometer and even down to the regime of 10 nanometer. That's what we are using. So that we believe that will help a lot in reducing the absorption loss. And of course, in the tandem, compared to single junction, the absorption loss is much relaxed compared to the single junction, right? Because there's only half of the spectrum coming to the poly, and the poly is mostly absorbing compared to heterojunction solar cell, which is absorbing a lot in the near infrared region, but poly is actually better in that aspect. So we think there's still great potential for the poly. Yeah. In terms of the opticals, I think we see advantages of using poly compared to TOPCon in terms of optics if we optimize it well.
Okay, great to hear that. Thank you.
Thanks.
If we don't have any other question, let's thank Heping again for the nice talk.